still should be able to compute, right? That's the way of surviving capital sequence. So throughout the sequence, a lot of people came to me and said, I don't understand what's going on. For a good reason. I have to admit, for a good reason, because capital sequence is really a sequence to teach you a lot of material rather than to explain where and how this material is coming from. So you're confused for a very, very valid reason. However, because majority of you are not coming from a math major, so you are not responsible for knowing how to derive those kind of things. So the primary goal for the capital sequence for all the other majors is to how to compute, is to get the application of calculus. So last lecture, we're talking about a vector field in R3. So this is a vector field in R3. And there are two major objects, operators we introduced. The first one is divergence. So the divergence is an operator that if you put in a vector field, you're getting a scalar function out. So this is going to be equal to partial f, partial x plus partial t, partial y plus partial h, partial z. So divergence of a function is extremely symmetric, right? So the x component, you hit it with x derivative and you sum them together. This will give you a scalar. So this is a scalar function. And the other operator we introduced that is so-called curl. So the curl of a function is equal to, in the very beginning, I know this is a vector field. So curl of a vector field is still a vector field. And we have the formula for the 3x3 matrix, right? I, J, K. Second row is, oh, I got my list of my favorite people to ask. Is George here? George. So what's the second row on that? So I have three rows to fill. Right? So this time I want to have F, G, H right here. In the middle row is going to be partial X, partial Y, and partial Z. Exactly. So this is a 3x3 matrix, and the curl is equal to is determined. So then we have the X component, the Y component, and the K component. So still, George, what is the I component?
Partial Y.
Partial Y hitting on H minus partial Z hitting on Z, right? So what's your J component? I already have plus right here, so you have to be very careful. So what is your J component?
Partial ZF.
Partial ZF minus partial X hitting on H. Very good. And your K component is going to be partial X hitting on G minus partial Y hitting on F. Okay, so this is the curl of the vector field. It is still a vector field. And also, we introduced this very convenient notation. This one is equal to the gradient dot product with F. Right? And this one is equal to the gradient cross product with F. So these two notations are not only convenient, but also it gives you a very good indicator. Divergence as a dot product, I'm getting a scalar, right? So dot product produces a scalar. Cross product is giving you a vector. So this is the definition for given a vector field, how to compute the divergence of the curl. The computation is actually pretty straightforward. One remark I make is the following. We know if the curl of a vector field is equal to 0, that indicates this vector field is irrotational and it is conservative, right? That's the one we learned. So if curl of F is equal to 0, then we know F is conservative. In other words, there exists a potential function such that this vector field is equal to the gradient of that potential function. Right? So here phi is a potential function. In other words, if this vector field is conservative, I can simply replace this vector field by the gradient of a scalar function. All right, so that's the only thing I'm doing here. So this means the cross product between the gradient vector and the vector field is supposed to be equal to the cross product between this gradient vector and the gradient of the potential. I'm simply replacing this f by gradient vector of a potential. All right, and this has to be equal to 1. Okay, and that's the only thing we did last class in terms of theorem. The theorem I want to mention is if you have a gradient vector, the curl is always equal to 0. Okay, so the curl is of a gradient vector field equals to 0. More strictly speaking, equals to 0 vector field, right? Because the gradient vector field is always a vector field. This guy is always producing a vector field. So strictly speaking, it's a 0 vector field. So last class, in the end of last class, I was trying to compute one problem. This is the problem I have. So I have a vector field which is defined by the cross product between 4, 0, 0 and x, y, z. Okay? It's the cross product between 4, 0, 0 and x, y, z. I want to immediately write down what it is. Let's write down the x, y, z components for this guy. Okay? Alan, is Alan here?
Yep.
Okay, so work with me. So I want to compute the vector field right here.
All right.
This is not quite convenient. So the best way we write is x, y, z, right?
Yeah.
And then I, j, k. So that will help you out later. What is the I component?
I component would be 0.
0. Y component is going to be x
Or z.
minus
Oh wait.
4z.
Yeah, my
And your k component
k component is for y.
for y. Okay. So this is basically a vector field. Andy, you have a question?
Yeah. Wait, what did you subtract it from?
Oh no, we're just computing the cross product between two vectors.
Oh, the cross product.
Okay, cross product of two vectors. And then I want to compute the curl of the vector field. So Ellie, work with me. Now I need to compute a 3 by 3 matrix. I, j, k, partial x, partial y, partial z, and the 0 minus 4z and minus 4, 1. Okay? So still 3 components. What is your I component?
It's partial y.
Partial y hitting on 4, 1, you're getting a.
Yeah, partial y for y.
So partial y hitting on 4y, you're getting a 4, am I right?
Yeah.
Basically, you're taking the derivative 4y with respect to y.
Okay.
Right? So it's just 4, and then partial z hitting on minus 4z.
Minus, so plus 4.
Plus 4. Okay? And j component is partial z hitting on 0, you're getting a 0, minus partial x hitting on 4y is
4y.
but this is a partial derivative with respect to x, right? Hitting on 4y is just a
So that's going to be 0.
0, right? So it's going to be 0 here. And last one, partial x hitting on minus 4z, 0, and partial y hitting on 0 is also 0. Okay? So in the end, I have a vector 8, 0, 0. So this example is straightforward. The only reason we're doing this is to practice how to do cross product. And then to review how to do cross product. Yep.
How do you get 0?
Which way? Which 0?
Right above?
This one?
No, the one above it.
This
That
one?
Yeah.
So this is the I component, right? So the cross product between these two vectors, the I component is the 2 by 2 determinant of this matrix.
So you basically did that, right? The
So-
matrix, basically.
Yeah, I did this matrix. Yeah.
Oh.
Right? When you do a cross product, it's much nicer to write it to these two rules, up and down, right? That will help you. This is actually a key component. If you want to do the cross product between these two, it's pretty hard to use the matrix structure, right? Questions? Okay, so at least the bottom line is, given any vector field, you should be able to compute its curl and its divergence, right? That's the bottom line. And then we will eventually introduce why we're interested in these two operations and how they're related to calculus. So one thing I want to also compute is the following. So I give you this formula. I also want to compute the dot product between a gradient vector and the curl of a vector field. Okay. First of all, this is making sense. It does make sense, right? Cross product, I have two vectors. And dot product, this is producing a vector. So I can do another dot product between two vectors. So this is at least making sense. Are you with me? Okay. And next, this is nothing but partial x, partial y, partial z, hitting on a new vector. And that vector, we already have it over there, which is partial, what is this guy? Already had it over here, right? This is what we have. So the x component is partial y h minus partial z f. Yes? What is my z component? Partial z f minus partial x h. And the key component is partial xg minus partial yf. Right? So we're simply doing the cross product between two vectors, the dot product between two vectors. Okay? Okay, so the fundamental thing you should get away from these two lectures is the following. We used to do dot product and a cross product for number vectors. Right? If you have numbers, then you can do the dot product, you get a number. You have number vectors, you do the cross product, you get a number vector. But the bottom line is we can do the same operations involving anything. You can put anything here to do the dot product or cross product. You're getting exactly the same principle. Okay, you use the same principle. If you do the dot product, you use the same principle as you're doing the cross product of numbers. Now with me? So that's basically what we're doing here. Basically, we're just doing the dot product between something which, even though they are not even numbers, but we can still do it. So the dot product is saying, I want to use this to hit on this one.
Shouldn't the partial z f, shouldn't that be partial z g? Or
Which one? This part?
yeah.
Did I come? Yeah, this is supposed to be g. Okay? And I have partial y hitting on this component and a partial z hitting on this component, and then I add them together. Yes? That's how we do the dot product. So I want a partial x hitting on partial y h minus partial z f plus partial y hitting on partial z f minus partial x h, then plus partial z hitting on partial x g minus partial y f. So this is simply following the dot product rule. Okay, you multiply these components correspondingly, and then you add them together. Okay, now I'm going to expand everything here. So the first term, I'm getting a partial x, partial y hitting on h. So I'm getting a second order derivative of h. Is this making sense to you? Questions? So this is nothing but partial square root of h over partial x partial y, right? This is nothing but a different notation, the same second order derivative of a function. Second one, I'm getting a minus x partial z hitting on f plus partial y partial z f minus partial y partial x h. Okay? So I have partial z partial x g minus partial z partial y f. Okay, so now we have 6 second-order derivatives, and then we will see whether we can cancel some terms. So second-order derivative hitting on h, I have this and which one? This one, right?
Yeah.
So I have second-order derivative hitting on h twice, but both of them are partial x, partial y, partial x. But when we did the partial derivatives, we know switching the order does not change the second-order derivative. All right? So these two terms are actually canceling each other. So the other two terms about f are these two. No, this is
YZ.
this is supposed to be t. So this is supposed to be t. So the two operators hitting on g, here is partial x, partial z, and here is partial z, partial x. So these two terms get canceled as well. And the two terms involving f are partial y, partial z, and partial z, partial y. These two terms are also equal to 0. So in the end, I have 0 in the end. So which is essentially saying the following. The divergence of a curve is always equal to 0. Okay? So there are two very nice theorems involving these two operations. The curl of a conservative vector field is always equal to 0, or the curl of a gradient is always equal to 0. And the other one is saying the divergence of a curl is always equal to 0. Okay? Equals 0, but this one is actually a 0 scalar. Okay? So the curl of a gradient is equal to a 0 vector field, whereas the divergence of a curl is equal to a 0 scalar. Okay? There's two things you can compute and help you to understand what they are talking about. You can ask yourself how we can do dot product, how we can do cross product, even though there's nothing about numbers involved here. You can still do the same thing, no matter what you stick in there. Okay? Any questions? Okay, so I want to mention one problem coming from the homework, and then we're going to move to the next section. So this example is asking the following question.